Hello calculus students, here we are with optimization problems. These are max-min problems. And we're going to start by doing an example, then we'll come up with a general process. Let's say a manufacturer wants to design an open box having a square base and a surface area of 108 square inches, as shown in this figure. What dimensions will produce a box with maximum volume? So the amount of cardboard you've got is limited, and you want to come up with the biggest possible box. So what we want to optimize, or maximize in this case, is the volume of the box. So you start with that equation. Start with a volume equation. Volume of a box like this is going to be the area of the base, x squared, times the height, x squared h. Now, we can't optimize it in two dimensions. We can't optimize it if we have three variables. So we have to use one of these equations to get rid of one of the variables. So this is called a secondary equation over here, because it's not the thing we're trying to optimize, but it will help us get this main equation, this primary equation, into just two variables. The volume, which we want to maximize, and let's say something like x. So we can solve this equation for h. 4xh equals 108 minus x squared, because we set the surface area, which is basically the area of the bottom, and the four sides, which are each x by h rectangles. Set that equal to 108, which is the square inches. And so h equals 108 minus x squared over 4x. And we can put that in for h over here. So that's where our volume equation comes from, that x squared times h, which is 108 minus x squared over 4x. And we can cancel out one of the x's here, so volume equals x over 4 times 108 minus x squared. And then go another step, and it's going to be easier to take a derivative, because that's essentially going to be our next step then. Take the derivative. This is going to be a volume equation with roots at 0 and the square root of 108 and 108. It looks something like this. It's a decreasing cubic. That much we knew from pre-calc concepts, that these two roots are at 0 plus or minus the square root of 108. What we couldn't get from pre-calc before is where is this maximum in, and this is the area that makes sense to us. This zero slope over here, that has to do with negative x's, and we don't want those. So we want to focus on this, but let's find out where that happens. So we're going to take this volume equation now. Sorry. Pin this down. Let's distribute first. Volume equals x over 4 times 108, so that's 54. It's 27x minus 1/4 x cubed. And now we take the derivative, key step. The derivative with respect to x on both sides, so we get 27 minus 3/4 x squared. And we set that equal to 0. It doesn't look like it's going to be undefined. So 27 equals 3/4 x squared. So 36 equals x squared. By both sides by 4 divided by 3. So x equals plus or minus 6. And so that's what we're looking for, that 6 right there. The square root of 108 or about 10, that was the root. Now we come up with that place where it's maximized. What dimensions will maximize the box? Now to further answer the question then, here's our x equals plus or minus 6. We don't want the negative 6, and we want the exact dimensions. So we look back to our dimensions chart, and that was x by x by h. X by x by h. And so we need that little formula again for what h is. Here we go. 108 minus 6 squared over 4 times 6. So 108 minus 36 over 24. And you get 72 over 24, or 3. So we get it for our third dimension there, 3. 6 by 6 by 3 will maximize the volume of the box. Okay. So you could have also put this in your calculator. I do want to see some sort of analysis of the derivative, whether you do the derivative by hand or with the calculator. I want you to show me how you're finding the derivative and set it equal to 0. And sure enough, here's our 6 by 6 by 3 giving the maximum volume of 108. All the other dimensions give volumes slightly less. So here's your guidelines. I talk about some of these things, the primary and secondary equation. Figure out what all your given quantities are and what quantities you have to be determined. Sketch with label measurements if possible. The primary equation is the thing you're trying to optimize, whether you're finding a maximum or a minimum. Now, I'll have the geometry formulas beyond and volume formulas that go beyond some of the basic boxes and squares and so forth. So don't worry about memorizing a lot of formulas. If there's something huge in a problem, I'll have that available. Then you might have to get the primary equation into just one independent variable. So that is the thing you're trying to optimize and the independent variable. Well, the primary equation we just saw might have 3 variables, so you need that secondary equation to sort of trim it down to one equation with just 2 unknowns in it. Look at the feasibility domain of the primary region. That's what we talked about, that we only wanted positive values for x. And then determine the maximums by calculus techniques. Okay? And make sure you look for all the critical numbers. Now let's look at finding the minimum distance, the points on the graph of y equals 4 minus x squared. What's closest to 0, 2? Here's 4 minus x squared. Here's 0, 2. We want to find the points that come the closest. So here's the distance formula. The distance between x, y, and 0, 2. And notice here's our problem again. We've got too many unknowns in this. We've got distance is unknown, and the x coordinate and the y coordinate. So this is our primary equation right here. And you want to minimize distance, have the closest point. So minimize distance d. Well, what do we have available to get rid of this? What could be our secondary equation? Yep, I think you're looking at it. There's your secondary equation. Because we can use that to get rid of one of the variables. We can replace y with 4 minus x squared. So d equals the square root of x squared plus y, which is 4 minus x squared, minus 2, all of that squared. So there's your equation. You can clean it up a bit. You don't have to for the calculator. X squared plus 4 minus x squared minus 2 is 2 minus x squared squared. And let's see what the TI-89 gives us for a derivative on this. Now you can certainly do the derivative by expanding this out and doing the chain rule and that type of thing. Let's take a look at the calculator's answer. It's also a good idea, let me give you a little tip here right now, the TI-89, is get this function listed in your y1 equals menu. y1 of x equals, and then put in there as left square root, and it'll put up the left parentheses for you, x raised to the 2 plus left parentheses 2 minus x raised to the 2 squared, and then in your parentheses. So that later on we can actually look at the function in the calculator's way and talk about some of the domain restrictions. Can you think of some domain restrictions right now? Think about what x is limited to. Well, it's pretty much, if we take any point on here, it's pretty much unlimited. The y's are limited, and we have to come down from 4, but we're looking at d as a function of x right now. So let's pause the tape for a second. Now in my TI-89, I set up a window of x's ranging from -2 to 2, because I looked here and it didn't look like it was going to get, it looks like it's getting farther away as I get out there. So I'm looking from -2 to 2. My TI-89 window, -2 to 2. And I set up the y's from 0 up to about 4, because I don't want to look at any negative distance, because this technically is d now, but in the TI-9 it's y. And I got a picture that looks something like this. So here we can see we've got some minimum distance here of x somewhere between 0 and 4, somewhere like in the 3 range. So it's nice to have that kind of idea of what's going on with the function. And you can see how the distance does seem to minimize in here. As we get close to 0, it starts getting bigger again. But as we start heading down the parabola, now it starts getting bigger again as well. So here's where it looks like it's smallest, and we have two possibilities here. One with the positive x, one with the negative x. So now let's do the derivative on the T99. You do the derivative, hit D, and now since you've looked at it already, you can just say y1 of x with respect to x. You don't have to re-enter it all again. So let's go to home screen and try that. And the 89 gives me this derivative. So d prime is going to be x times 2x squared minus 3 all over square root of x to the fourth minus 3x squared plus 4. I think you'll see that that x to the fourth minus 3x squared plus 4, that's basically what this gets when you expand it. We get some extra terms in here because you're taking the derivative of the inner function. So, you can tell from the graph, though, that we don't look like we're concerned with any undefined sections here. So I'm going to focus on what makes the numerator equal to 0. And so the numerator equals 0. We set the derivative equal to 0, and to do that I'm going to set the numerator equal to 0. So we get x equals 0, or 2x squared minus 3 equals 0. X equals 0 gives us this thing that's giving us a sort of a relative maximum distance there. We want these relative min distances, so 2x squared equals 3, x squared equals 3 halves, so x equals plus or minus the square root of 3 halves. Okay, now you can put this 3 halves back into the distance equation, and that's where you get this 5 halves. So that minimum distance is 5 halves, 2.5. Now let's look at a minimum area problem. A rectangular page is to contain 24 square inches of print. The margin at the top and bottom would be 1.5 inches. The sides are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? Okay, so we have to have 24 square inches of print. So this is fixed. So how should we set up the page XY so that we use the minimum amount of paper? So here's our primary equation again. Because this is the area we want to minimize. And it's x plus 3 by y plus 2. That's because this y, you have to add on an inch margin on either side, and this x dimension, the height, you have to add on 1.5 inches on each side. So you want to minimize this area. Now, we're going to need a secondary equation because we have 3 variables here. So let's look for the other information given, and here it is. 24 square inches. This will create our secondary equation. That you have 24 square inches of print. So x by y has to equal 24. So we can get rid of one of our variables here and say y equals 24 over x and put that in for y. So area will equal x plus 3 times y, which is 24 over x plus 2. Now it's up to you how you want to try and take the derivative of this. This one looks like it's pretty easy to do by hand, because especially if we just FOIL it out, area equals, first would be 24, outer would be 2x, inner would be 72 over x, and last would be 6. So you get the area is 30 plus 2x plus 72x to the negative 1. So when you do the derivative, you get 0 plus 2 plus negative 72x to the negative 2. So we get the area is 2 minus 72 over x squared. You can see that we get one critical number then. At x equals 0, that will make the derivative undefined. We should investigate that. The thing is, does x equal 0 make sense for this problem? No, we're not going to get any areas. So then the other critical number, let's set the whole thing equal to 0. And so we get 2 minus 72 over x squared equals 0. 2 equals 72 over x squared equals 36. So you get x equals plus or minus 6. And a negative x doesn't make sense, so x equals 6 seems to be our answer. And sure enough, when x equals 6, y, remember, was, I believe, 24 over x, right? So we get 24 over 6, so we get 4. So the dimensions of the paper itself then, the whole paper, the whole page, by y plus 2, so that's 6 plus 3 by 4 plus 2, or 9 by 6. Should give us the minimum. Now, you might want to take a look at a picture of this, somehow decide, does this actually give us a minimum or maximum? Because all we did was you said the derivative was equal to 0, right? So one way you can check this is by doing the second derivative test. Because it's fairly easy enough to take our derivative here, and let me just cut that one out. What happened there? Cut. There we go. That's our area. That's our first derivative. So now when we do the second derivative, it'd be 0 minus, remember there's x to the negative 2, so it'd be minus 72 negative 2 x to the negative 3. So we get the second derivative is 144 over x cubed. And the second derivative at x equals, we came up with our answer of at 6 is 144 over 6 cubed, which is positive. So by the second derivative test, at x equals 6, we have a relative minimum. Because if the second derivative is positive, the function is concave up, so that means we've got a relative minimum. Okay. Let's find a minimum length here. Two posts, one 12 feet high and the other 28 feet high, stand 30 feet apart. They are to be stayed by two wires attached to a single stake right there, running from ground level to the top of each post. Where should the stake be placed to use the least amount of wire? So the quantity to be minimized is the length of wire used here. And you can see that x varies between 0 and 30, and so y will vary too, and so will z. And so the amount of wire we use, our primary equation then, is going to be the amount of wire that we're using, which is y plus z. X seems to be our key independent variable there. So we write x as this distance, so 30 minus x is the other distance because we're told that they're 30 feet apart. And so, how can we're going to have several secondary equations. Because we want to get w just in terms of one variable, I would think it would be x. Well, that's where we can use the Pythagorean theorem. X squared plus 12 squared equals y squared. And we get 30 minus x squared plus 28 squared equals z squared. There you go. And it's just a matter of solving each of these for y and z. So y equals the square root of x squared plus 144. And z equals the square root of 30 minus x squared plus 28 squared, which is 784. That's going to make a bear of an equation, but we can So our primary equation, w equals y plus z, becomes square root of x squared plus 144 plus the square root of 30 minus x squared plus 784. I think we're going to ask the calculator to do the derivative on this one. Okay, so I put this in my calculator on the TI-89. With a window of, when I look back at the problem. If you look back at the problem, you can see x, it's got to be a positive number, it's a distance, and it's going to be at most 30. So our window for there makes sense to have x go from 0 to 30. And for our w, which is y in the calculator, 0 up to, I just did a quick estimate here, if this is 30 along here, I don't think we're going to use much more than 60. So 60 should work out well. And when I did that, I get something that looks like this. So suspecting some minimum in here somewhere between 0 and 30. Closer to this side and this side. That kind of makes sense. Okay. Now let's see what the calculator says the derivative is. And I get for the derivative w prime x minus 30 over the square root of x squared minus 60x plus 1684 plus x over the square root of x squared plus 144 square root of x squared plus 144. That's a big nasty equation. And we want to know when that's 0 and undefined. Well, actually, if I'm looking at my picture, I can tell we're not going to be looking at any of the vertical asymptotes here. So I'm not concerned so much where the derivative is undefined, but where is it going to be 0? So we can try and set this whole thing equal to 0. Now, as you can see, that's going to be a bear of equations solved algebraically. I mean, there's some cross multiply and square you can have and so forth. But let's go ahead and use the solver feature on our calculator in this. And let me show you a little tip about how you can save some time, especially if you've already graphed this in terms of the solver. Let me show you what you can enter. You can't use poly because it's not a polynomial equation, but here goes. Okay, so here's what I put in the solver on the TI-89. Solve, parentheses, the derivative of y1 of x with respect to x. I set that equal to 0, and I had to solve for x. And it gave me this answer of x equals -9. Now, if I want the other answer, I might want to just graph the derivative and see, but you see it ends up being negative, and that's outside the domain of consideration here. Another thing to be careful of is, note the endpoints here. The domain restriction on x is from 0 to 30. You should check those to make sure that they're not less. Because remember from our extreme value theorem, you're going to have a maximum and a closed interval and a minimum. Doesn't necessarily happen to have the critical values. So you should check the endpoints. Now, I'd consider this graph a good enough check of the endpoints. You can see that this is clearly below these two endpoints. So the wire should be staying at 9 feet from the 12-foot pole. All right, and here's where we talk about the technological applications there. Notice you don't have to actually expand this all out when you're doing it. It made some sense in this case, but the calculator can expand things out for you too. And there's that minimum value. Okay. Now let's do one example where you have an endpoint maximum, which is what we're just talking about. 4 feet of wire is to be used to form a square and a circle. How much of the wire should be used for the square and how much should be used for the circle to enclose a maximum total area? So here's the quantity to be maximized. X squared plus pi r squared to maximize that. So that's our primary equation. We need the secondary equation I'm sure you remember from, we're going to have to get a perimeter here. The perimeter is 4x and the circumference is 2 pi x. So the perimeter is going to be our secondary equation. So let's work on the secondary equation over here. This is our primary right here. We want to maximize the area. Secondary equation is the fact that we're using 4 feet of wire. So the perimeter plus the circumference of the circle have to equal 4. So 4x plus 2 pi r have to equal 4. So we want to solve this for r as a function of x. So we can plug it into here. So 2 pi r equals 4 minus 4x. So pi r equals 2 minus 2x, or r equals 2 minus 2x over pi. And that's what plugs in for r right there. So our new primary equation now is x squared plus pi times r, which is 2 minus 2x over pi, all that quantity squared. Now, this one I'm actually going to do by hand because it's not that bad. It's just a quadratic. It just has some strange coefficients. So the area is going to be x squared plus pi times, expanding out the top, 4 minus 8x plus 4x squared all over pi squared. And so area equals x squared plus, now let's distribute the pi divided by the pi somewhere else. So that's 1 over pi times 4 minus 8x plus 4x squared. So the area is x squared plus 4 over pi minus 8 over pi x plus 4 over pi x squared. I'm actually going to put it in the form of a quadratic. 1 plus 4 over pi x squared plus negative 8 over pi times x plus 4 over pi. And I just bring that up because you don't always have to use calculus if you recognize that this is your old friend, the parabola. It's a quadratic function, and the maximum will occur at negative b over 2a. So that's negative 8 pi over twice 1 plus 4 pi. I can calculate that out. And we get 4 over pi plus 4, which is about 0.56. Now that's where the derivative is. That's where the minimum, though, that's where the vertex occurs. But notice that this is a happy parabola because of the positive coefficient on a. So it's going to look like this. So this is a minimum. And we're asked to find the maximum area. So we have to consider the feasibility region here. And the feasibility domain there is from 0 to 1. Look back at the picture. We certainly don't want to have negative values for our area or for our sides. So, and we can only go as high as 1 because the perimeter of the square, if this perimeter, if the whole 4 feet is used for the square, you get x equals 1. So you can't go any bigger than 1. So that's why the domain restriction on x is going to be from 0 to 1. So when you check those endpoints, notice you get this. Gives a much bigger area. When the x equals 0, you're basically putting everything into the circle. Because basically a circle is going to be more efficient in enclosing area than a square is. So be careful of that when you're doing these problems. Okay? Now if I had said find the minimum, yeah, then our minimum would be here at 0.56. Okay, here's just some of the big primary equations we set up as a result. And it can get that complicated, and even more so in real life problems. Okay, flange out.